So, for this topic is the Earth's energy, radiation budget, and greenhouse effect. So the Earth budget refers to the tracking of how much energy is flowing into an out of the Earth planet. So almost all of the Earth's surface energy comes from the sunlight, right? So without the sun, the Earth will be freeze and freeze over, and it have a temperature below minus 260 degrees Celsius, right? So the energy entering reflected, absorbed, and also scattered by the Earth system. So the Earth energy budget refers to the tracking of how much energy is flowing into and out of the Earth's climate. So when the energy is going, right? And if the energy coming in balances with the energy going out, and that the Earth receives energy from the sun's, and it also reflects the radiated energy back into the space. So this balance of incoming and outgoing energy creates our climate that supports life as we know it on the Earth. So the law of conservation of energy states can neither be created nor destroyed, right? So, but it can be transformed from one state to another. So the energy from the sun is delivered and light energy. It's the light energy. So, and some of the energy is used to warm the air, and the differences in densities of air and water between warm and cold regions of the atmosphere and oceans induce currents. So, and also heat. So heat also drives the evaporation of water from the oceans and drives the water cycle. So some light's energy is converted into chemical energy through photosynthesis. That photosynthesis and stored as biomass, right? So all of the energy that forms the atmosphere, oceans, and land must be radiated back into space in order to maintain our current climate. The amount of energy radiating back into space in order to maintain our current climate. So if the amount of energy radiating back into space that is decreased by even a very small amount, so it can lead to warming, right? So it is believed that increasing levels of carbon dioxide, CO2, so in the atmosphere, it has a greenhouse effect of reducing the amount of energy radiated back into space, right? So the reflected means, it means, for example, it is mirror, right? So in mirror, you looking at a mirror, your image reflected back to you from the mirror, right? So in this sense, some of the radiant energy entering atmosphere from the sun, that is in in fact, reflected back, right? So if we think about the sun, so here is atmosphere and there's some clouds in the atmosphere. We have some solar radiation that comes through. We have some solar radiation that is reflected back out into space. So, but not just from the clouds, but also from the dust particles and dirt particles in the atmosphere, right? So the dust and dirt in the atmosphere will also reflect some of that radiant energy backward. So while some is getting through and going all the way down to the surface. So what is absorb? Absorb means that there is an energy transformation. Energy transformation. And this energy transformation is going to be radiant energy to thermal energy or heat energy, right? So which is absorbed by the surface. Okay? So you see here, incoming solar radiation. Incoming solar radiation. So it's called short wave, S-H-O-R-T, short wave radiation, right? So most of the incoming energy is in short wave from such as ultraviolet rays and visible rays. So from the sun drive the climate system, right? So some of this incoming radiation is reflected off clouds. Some is absorbed by atmosphere and some passes through the Earth's surface, right? So approximately globally and annually, 50% of the solar radiation strikes the Earth and its atmosphere is absorbed at the surface, right? So the atmosphere absorbed 19% of incoming solar radiation, and the remaining of 30% is reflected back into the space. So the shortest wavelengths of solar radiation, those are absorbed by molecules in the upper and middle atmosphere. So in particular, the ozone selectively absorbs ultraviolet radiation while allowing visible radiation to pass through relatively unhindered. So the reflection significantly affects the solar radiation that reaches the ground, as the sun's rays could be reflected off of air molecules, and clouds are the ground itself. So light-colored or shiny objects reflects more radiation than dark objects, right? So energy that is reflected cannot be absorbed or transmitted through an object that is dark color, right? So you see in this incoming solar radiation picture. In this picture, you can find incoming solar radiation, right? And outgoing solar radiation, you see here. So the yellow color, this yellow color arrow shows incoming radiation. So this red color arrow shows outgoing radiation, right? So outgoing energy, sorry. So now you see the first important thing is, let's understand it form of this 100 unit. You see, this 100 units of energy that is received from the sun, right? Received from the sun. So consider the insolation received at the top of the atmosphere is 100 units, right? So now let's divide it in these 100 units in different segments and understand how it is divided. And finally, how these 100 units incoming is actually equivalent to 100 output, right? So now you see, while passing through the atmosphere, Here what happened? There are these processes such as reflected, scattered, and observed. So all these processes happens here. So roughly what happens? So 35 units. 35 units. Now remember this out of 100 units, right? Out of 100 units, 35 units are reflected back, right? So what is left is 65, remaining 65 units, right? So 35 is gone, 65 is remaining. So 35 are reflected back to the atmosphere, right? So even before reaching the Earth's surface. So if you want to learn about the bifurcation of this 35, right? So leave that 65. Now, this 35 units bifurcation. So in the 35 units, 6 units are scattered into the space. So 6 units are scattered into the space. In 27 units are reflected back from the top of the clouds only. So the atmosphere are clouds, right? And 2 units, meaning 2 units from the snow and ice covered areas of the earth also go back. So that is important. The next, these 35 units are gone out of 100, right? So from what we receive already, right? So now what is remaining? 65, right? 65 units. So that this reflected amount of radiation is that the units are called albedo, right? Albedo. So now what is the albedo? Albedo is the portion of the incident radiation of the energy and reflected back from a surface of a body is called albedo or reflection coefficient or simple reflectivity, right? So albedo, reflection coefficient, remember these terminologies. Reflection coefficient is also the albedo only, right? And simply reflectivity. So it is written reflectivity or it is written albedo or it is reflection coefficient. Remember, it is talking about same thing, right? So albedo can be simply defined as a measure of how much light that hits a surface is reflected back without being absorbed, right? So albedo is an important concept in environmental management and also climatology and astronomy also. So, and it plays a major role in the energy balances of the Earth's surface as it defines the rate of the absorbed portion of the incident solar radiation. So how much is absorbed about how much is reflected back by the what surface on the earth, right? So every surface, remember, every surface have a given value, right? So someone has lesser albedo values, or someone has greater or higher albedo value, right? So what is the albedo? It is the on top reflection. It means body reflection, something, right? So it is reflect 5% or 4% or 1%, right? So more reflection value means more albedo value. So reflection coefficient is more. It means it has more tendency to not absorb rather than give away. So in heat budget, so what is the importance now? You can understand that heat budget is now talking and giving out. So it will depends upon this surface property, right? Right. So you see here what is happening to this remaining 65. 35 is over and remaining is 65. So because 35 units are already gone, right? So out of this 65, 14 units, right? 14 units are absorbed within the atmosphere, remember? So when it is reflected back 35, right? So the remaining 65 is there, out of which absorption happens now. So no reflection, right? Remember, absorption only. So absorption happens for 14 units where in the atmosphere, and rest of the 51 units by the earth surface. That is important. So the earth radiates back those 51 units now. It's because of what reaches finally the earth. So that is this 51 units, right? So it is obviously reflected back this 51 units only. So now these 51 units are radiated to space in the form of terrestrial radiation. Terrestrial radiation. So this is what we say, the terrestrial radiation. So that heated earth becomes a radiating body and it radiates energy to the atmosphere in long wave form. So this energy heats up the atmosphere from below or down. So this process is known as terrestrial radiation, right? So this terrestrial radiation, what we need to learn out of this 51 units, right? Out of these 51 units, so what is the bifurcation for that? 17 units. 17 units are radiated back to the space directly, right? And what is the remaining out of this 51? 34 units, right? So 17 are already radiated back and 34 units are left here. So which are absorbed by the atmosphere while they're going back. So atmosphere is very interesting, right? So while it is talking and get something. So while it is given out, it is also get something. So at both these stages, incoming stage as well as outgoing stage, atmosphere actually absorbed, right? So now let us, this 34 units absorbed by the atmosphere, right? So now this 34 units bifurcation is 6 units absorbed by the atmosphere directly and 9 units are for convection and turbulence and 19 units are for latent heat of condensation, right? So finally, the 48 units are absorbed by the atmosphere if you are looking in the total 100 units, right? So where you remember first the 14 units from the insolation and 34 units from the terrestrial radiation. So this is from the 48 units, right? So the atmosphere is the greatest absorber. So this is important. So the total 48 units of the solar insolation is single-handedly absorbed by the atmosphere itself. And also the same amount is radiated back to the space, right? So now you see here, the total radiation returning from the Earth and atmosphere respectively, how much? Now, this 48 is coming from the atmosphere and 17 is going back into the space. So the total amount is what? 17 plus 48 is equal to 65, right? So now coming back to this same 65 units where it started, right? So this is the entire balance, right? So the entire balance between the 65 incoming and 65 outgoing out of the 65. This is the bifurcation, right? So the balance total 65 units are received from the sun. So this balance sheet is called heat budget, and also called as heat balance of the Earth. So now what we need to do is make a summary. You see here, this is the final summary per 100 units. So in this summary was what was the incoming and where were the expenditures, right? So the amount of incoming solar energy at the top of the atmosphere is 100 units or 100%, right? So which means 100 of sun rays are hitting the exosphere. It is the first outermost layer of the atmosphere, right? So now while passing through the layers of atmosphere, some amount of energy reflected, right? And scattered and absorbed. And only the remaining part reaches the Earth's surface, right? So the 35 units of sun rays are reflected back into space even before reaching the Earth's surface. So this 35 units of reflected radiation is called the albedo, right? ALBEDO. Albedo means how much of the sun's energy reflected back into the space, right? So now, as the remaining of 65 out of this 100, right? So 65% or 65 units sun rays enters the atmosphere, and in this 65 units, 14 units of it is absorbed within the atmosphere by the water vapor, dust particles, and also other atmospheric gases, right? And now the remaining 51 units, 65 minus 14 equal to 51, right? Remaining 51. So 51 units of sun rays is actually absorbed by the Earth's surface. So now it's time for the Earth to radiate back the 51% of heat, so which is received from the sun, right? So in other words, we can say it's time for what is the terrestrial radiation, right? So this time the heat travels in the vertical manner, and there is a term given to it. It's called convection, right? Convection. So as the heat rises, 34 units of the heat will be absorbed again by the atmosphere, right? So which includes water vapors, dust particles, horizontal air movement, and also other atmospheric gases, right? So the remaining 17 units of the heat is radiated to space directly, right? So if you notice here, in total 48, these 48 units of heat is absorbed by the atmosphere, that is 34 units, right? It is 34 units from the terrestrial radiation and 14 units from the incoming solar energy. And this 48 of heat absorbed by the atmosphere is also radiated back into the space, right? So now the total radiation is 48 units plus 17, this 70. This 48 plus 17 equal to how much? 65 units. So, and if you remember in this beginning, we have that 65, this 65 unit of heat makes it into the atmosphere, right? So now what we can conclude from this calculation is that if the amount of heat received in the form of undulation equals the amount lost by the Earth through terrestrial radiation. So which in this case, we found it to be equal. That means the Earth maintains its temperature, or we can say the Earth neither warms up too much nor cools down too much, despite the huge transfer of heat that takes place, right? So this is the heat budget of the Earth. So while outgoing radiation is infrared, from such as infrared rays or radiations. So this radiation is also called as long wave. What is that? Long wave. Incoming radiation also called as short wave. So this is long wave radiation. So the Earth's surface, atmosphere, and clouds emit radiation in the infrared band and near infrared band, right? So the outgoing infrared radiation from the Earth's surface, that is also called terrestrial radiation, right? So that is selectively absorbed by certain molecules, such as the particularly water vapor and carbon dioxide, right? This water vapor and carbon dioxide. So gases which absorb infrared radiation are termed collectively as greenhouse gases, right? Greenhouse gases. So water vapor and carbon dioxide emit infrared radiation, right? So infrared radiation from greenhouse gases in the atmosphere that is emitted in all directions, right? All directions. So including back to the Earth's surface. So it is this re-emission to the Earth's surface that maintains a higher temperature on our planet than what would be possible without the atmosphere. So the considered water is also an efficient absorber and emitter of infrared radiation. Thus, clouds act in a manner similar to greenhouse gases. So the major atmospheric gases, what are the major atmospheric gases? Those are oxygen and nitrogen, right? So these are transparent to incoming sunlight, but are also transparent to outgoing thermal or infrared radiation, right? So, however, the water vapor and also carbon dioxide and methane and also other trace gases are subject to many wavelengths of thermal radiation, right? So the increasing concentration of greenhouse gases like carbon dioxide, methane increase the temperature of the lower atmosphere by restricting the outward passage of emitted radiation that is resulting in global warming or global climate change. So when greenhouse gas molecules absorb the thermal infrared energy, right? And also their temperatures will be rise. So these gases then radiate an increased amount of thermal infrared energy in all directions, right? So the atmospheric heat budget of the Earth depends on the balance between insolation, that is incoming solar radiation, and outgoing terrestrial radiation. Right? So this is the Earth radiation budget is the balance between incoming energy from the sun and the outgoing long wave and reflected short wave energy from the Earth. So this is the Earth energy budget and radiation budget, right? So now, climate system. So Earth climate arises from the interaction of four major climate system components, that those are lithosphere, atmosphere, biosphere, hydrosphere, right? So remember, all of the Earth systems end with the word sphere, S-P-H-E-R-E, the sphere. Right? So they're often also called the four Earth spheres, that is called Z, like Z, right? So the Earth is interconnected to these cycles, right? So these systems work together to create our world. So climate is the average weather. It means the average state of the atmosphere for a given time scale, right? That is, time scale means hour or day or month or season or year decade, right? So typically over a period of 30 years, and it is determined by a combination of processes in the climate system, such as ocean currents and wind patterns, right? So the circulation in the atmosphere and oceans is primarily driven by solar radiation and transport heat from the tropical regions to regions that receives less energy from the sun. So the water cycle also moves energy through the climate system. In addition, different chemical elements necessary for life, so those are constantly recycled between the different components, right? So you see this picture also, the climate system can change due to internal variability and external forcing. So these external forcing can be natural, right? So such as variations in solar intensity and volcanic eruptions and are caused by humans, right? So the accumulation of heat trapping greenhouse gases mainly being emitted by people burning fossil fuels. So that is causing global warming, right? And human activity also releases cooling aerosols, but their net effect is far less than that of greenhouse gases. And changes can be amplified by feedback processes in the different climate system components. Okay. So what are the components of the climate system? You see here, this one, atmosphere. First one is atmosphere. It came from the word atoms, 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 which means steam or vapor, right? Steam or vapor. Right? So the Earth atmosphere envelopes the Earth and extends hundreds of kilometers from the surface. Right? So the atmosphere is the body of gases that surrounds our planets. Right? So the atmosphere contains mostly of nitrogen is 78%, oxygen is 21%, and remaining 1% is called trace gases. Those are argons, right? So it is including water vapor, ozone, carbon dioxide, and also methane, which absorb and then release energy as infrared radiation. So in the atmosphere, water vapor and carbon dioxide, so those are the gases most important for the working of the climate system, right? So gases in the atmosphere keep the average temperature of the lower atmosphere. It is a habitable 14 degrees centigrade or 570 degrees Fahrenheit to a process known as greenhouse gases, which allow visible light from the sun to penetrate the surface, but block some of the infrared radiation the Earth's surface emits to balance the sun's radiation. So this radiation causes rise the surface temperatures, right? And the hydrological cycle is the movement. Right? So it is the movement of water through the atmosphere. So not only does the hydrological cycle determine patterns of precipitation, and it also has an influence on the movement of energy through the climate system. Right? So the gases in the atmosphere play other roles as well. For example, ozone. It means O3, right? So O3 is within the upper atmospheres, that is ozone layer, protects life from harmful doses of solar radiation. And carbon dioxide also. Carbon dioxide is also used by plants for photosynthesis. And water vapor, it condenses to form the clouds and precipitation that form our weather, right? And next, hydrosphere. So hydrosphere came from the word is hydra or hydro. So it is the Greek word, right? Hydro means water. All of you know about this. Hydro means water. So it includes all the water covering the air, both liquid or solid gases, solid forms, right? So it ranges from the 10 to 20 kilometers in thickness. So it is the from the depths of the ocean to the ice-capped peaks of the mountains. Okay? And it is the component comprising all liquid surface and subterranean water and both fresh water, including rivers, lakes, and aquifers, and also some of the saline water of the oceans and seas. So the fresh water runoff from the land returning to the oceans, right? In rivers influences the ocean's composition and circulation. So the oceans cover approximately almost 70% of the Earth's surface. So what is the ocean circulation? Ocean circulation serves to transport heat from the equator to the poles, right? So in addition, gases from the atmosphere, it can dissolve in the ocean and be stored for many years in its depths. right? Many years in its death. So however, when too much carbon dioxide is dissolved, what happens? Seawater becomes more acidic, making it harmful to marine life also, right? So an important process that happens in the hydrosphere, that is the water cycle. So the water cycle describes the continuous movement of water on and above and below the surface of the earth, right? So this is the hydrosphere and cryosphere. So in some books, cryosphere falls under the hydrosphere, right? So the cryosphere contains all parts of the climate system where water is solid. It means it is the frozen parts of the water. So this includes such as sea ice and ice sheets and also permafrost and snow water, right? Because there is more land in the northern hemisphere. Northern hemisphere. It is compared to the southern hemisphere. So it is a larger part of that hemisphere is covered is snow. Is that snow? So most frozen water is contained in the ice sheets on Greenland and Antarctica. So which average about 2 kilometers in height. So these ice sheets slowly flow towards their margins. So these ice sheets with their bright white color, ice and snow, that is reflect large amounts of incoming solar energy back to space. So ice also serves to insulate the ocean and land from the atmosphere. So the presence of ice can change the dynamics of wind and weather processes, right? This is the cryosphere and lithosphere. Lithosphere, it came from the Greek word lithos, which means rock. So the lithosphere, the latest sphere, it includes the rocks. So it means includes earth crust and upper part of the mantle, and it make up the lithosphere. So that's why it is also called as the crustal system also. So some people says they call lithosphere as geosphere, right? So however, there is a minor difference between the lithosphere and this geosphere, right? So the lithosphere is rigid and mechanically outer layer of the earth, and it is divided into 12 major plates. And now other hand is geosphere. It is the solid body of the earth. So for these classes, we are just going to use lithosphere for the latest sphere, hydrosphere and atmosphere. So we are going to use lithosphere to avoid confusion. Okay. So the lithosphere is the land surfaces such as soil and rocks, right? And human-made surfaces such as roads and buildings. The different material that make up the lithosphere absorb different amounts of energy from the sun, while mountains can slow or redirect winds and affect where rain falls, right? So our lithosphere consists of approximately the first 60 miles, first 60 miles of solid material from the surface of the planet down. So this is also referred to as earth crust, right? And the one important process that happens in the lithosphere is the tectonic. What is that? Tectonic activity, right? So the tectonic activity describes the interactions of huge slabs of lithosphere, are commonly known as tectonic plates, right? So these tectonic activities are the one responsible for some of the geological events such as earthquakes and volcanic eruptions and also volcanic formations, right? So, and it is driven by the Earth's internal heat, and it is said that the Earth's internal heat flow to the surface. So this thought to be how much 80% due to mantle convection. So the mantle convection describes the movement of the mantle as it transfer heat from the inner core to the lithosphere, right? So the lithosphere constantly changes because of shifts in the tectonic plates. So a volcanic eruption affects all of Earth's spheres, right? So the magma coming up through the Earth is part of the lithosphere. Remember this word? So the gases and materials from the eruption move from the lithosphere into atmosphere. So when the lava pouring down the volcano will change the biosphere, right? So while the condensation of water alters the hydrosphere, right? The next biosphere, this is the last one in this climate system. So it came from the root. So bio means life. So it also interacts with the rest of the climate system. So bio means life. It contains all of the life on the earth, right? So the biosphere refers to living things that are found on the earth. So even on the parts of that appear to be uninhabited. So the biosphere overlaps the atmosphere, lithosphere, and hydrosphere. So we are part of the biosphere, right? Is it correct or not? Right? So as are the crops that we grow and pets that we keep, every living being from tiny bacteria to blue whales is part of Earth's biosphere, right? So the earlier life from is about 3.5 to 3.7 billion years ago, and these are the micro organisms. That is called microorganisms. So one type of microorganisms that forms are prokaryotes. Prokaryotes, right? So these are survived without oxygen. Remember this. So now we call them an aerobic microorganisms also. So in the biosphere, there are different ecological communities we can call biomass, right? We can call biomass, BIOMAS, biomass. So some example, the tropical rainforests and also tundras and deserts. These, right? So we can find some living things on the desert, but we cannot find them on tundras, right? So the biosphere is considered as carbon dioxide sink of the earth. So a carbon sink is actually aggressive. So that is what absorbs and stores the atmosphere's carbon. So remember, this is not a carbon source. It actually gets the carbon only, right? So now there are two types of carbon sinks, that is natural and artificial. So for example of this natural carbon sink is a tree or forest, right? So that is natural. So they absorb carbon dioxide from the air. And artificial carbon sinks are of course, man-made, right? So example is a process called artificial carbon sequestration. Artificial carbon sequestration, right? So now, this carbon sink is important for the carbon cycle. So now this carbon sink is important for carbon cycle. So this diagram shows the carbon. So, but it's not important in this lesson, but I already told about this cycle in previous class, that is carbon cycle, right? So this is another topic. So it is the biogeochemical cycle by which carbon is exchanged among the biosphere and geosphere and hydrosphere and also atmosphere of the earth. So basically it is the natural way of reusing the carbon atoms, right? So in this figure, each of the earth sphere, this could be represented by the figure. So the double-headed arrows here, you see, indicates that the cause and effect relationship of these interactions go in both directions, right? So the event affects the hydrosphere, but in turn, the hydrosphere will give something. So it is a mutual relationship between the event and hydrosphere, right? You see. Or any other spheres or any other systems. So let's have, for example, an interaction between this hydrosphere and an event on May 18th, 1980, when Mount St. Helens erupted. So this is our event. So this is event altered the surroundings, right? Surrounding environment. In this case, the hydrosphere. So it could be the ocean, the river, or anything. So maybe the water became polluted, right? So there are some interactions that occur among the spheres themselves, the 10 types of interactions. So that can occur within the Earth system, often occur as a series of chain reactions, right? Chain reactions. So it means that one interactions lead to another interactions, right? So it leads to another interaction, right? So, for example, while ago the event hydrosphere that affects the lithosphere, yeah, right? Or event hydrosphere affects the biosphere. So it is like a ripple effect or domino effect, right? So let's have, for example, of volcanic then complex interaction. So the volcano from the lithosphere, it may emit large quantities of sulfur dioxide, which will affect the atmosphere, right? So when these sulfur dioxide combines with water, what happens? There are sulfuric or sulfurous acids are formed, right? So the rain may bring these acids to the earth. So that is acidifying soils, lakes and rivers, which are part of our hydrosphere. And now the acidic water, right? Acidic water leaches nutrients from the soil, that is lithosphere, into the water table, that is hydrosphere, and which makes the soil less fertile for plants, this biosphere, and the water supply, that is hydrosphere, would also be less potable for humans, that is biosphere. So in the so in that one scenario, 3 spheres already interacted. So this acid rain will soon fall to the lakes and bodies of water, which reduces the pH, right? pH of the water. So when the pH of the water decreases, making it more acidic, some life forms might be affected. For example, what is the phytoplankton and zooplankton? So now the photosynthesis is reduced carbon dioxide, right? So it can build up, and again, if carbon dioxide increases, it will result to global warming, which is global warming. So which is the atmosphere, right? So this in turn may contribute to increase melting of glaciers, that is hydrosphere. So you see how one event affects the whole system here, right? So for example, I can say one thing. So now you are in biosphere, right? So you are in biosphere. When you went out in the early morning, snow is falling down drop by drop, that is cryosphere. And you can jogging on the ground, that is lithosphere. And you want some air, it means breathing, that is the atmosphere. And you want to drink some water, that is hydrosphere, right? So this is, so we could not exist without any one of these systems, right? So our planet's climate depends on the whole Earth system. So the sun and land and ocean, ice and living organisms. So these are interact with the atmosphere as part of the climate system in many complex ways, right? So these systems all interact, create and maintain the world as we know it, right? So this is the climate system topic, okay? So you must remember these 4. You can write in your examination. So don't write climate change. So climate system is different and climate change is different, right? So some people are confused about this climate system and climate change, okay? So I already told that is climate change, okay, about that. So now you can write, so these four systems are 4 spheres in your examination one by one. They're asking in of 15 marks question, okay? So you can write, so atmosphere is air, cryosphere is snow and ice, And biosphere is living things, and hydrosphere is water, and lithosphere is solid earth. So this earth. So these are our planet climate depends on the whole earth system, right? So components are, you can write also components of this climate system. So you write one by one: atmosphere, hydrosphere, cryosphere, lithosphere, and also biosphere, right? And you can write also chain reactions. So how event interact with one to another direction, right? So this is the chain reaction. So this is very important question in your examination. Okay. So you can write these 4 spheres. Okay. And also you can write this volcano, how to interaction with this spheres. Okay. So you can write these examples. Okay. So acidic water, that is lithosphere, hydrosphere, biosphere, hydrosphere, and biosphere. Come again. Biosphere, right? So this one. Okay. So this is the climate system topic. So any doubts, can ask me.